In this video, we're going to cover three different AP Calculus sections, 1.9, 1.10, and 1.11. In 1.9, this is just kind of a culmination of what we've done in the past several sections of Unit 1. And this is connecting multiple representations of limits. Really, all I'm going to do in this section is remind you of the three different ways we have found limits so far and talk to you about when you would use each one. There are three methods: analytical, graphical, and a table. Okay, they are listed here in the order that I would do them, in the order that I would try them. I will only do a table if there's no other way to find the limit, because tables are time consuming and we're dealing with a lot of messy numbers, decimals that go on forever, irrational numbers. So we only want to use this if there's nothing else available for us to use. Analytical is the simplest method, so we will always use that first. The first thing I am always going to do is I'm going to try to plug that number in, whatever x is approaching, into the function to see if it gives me a nice number that I can deal with. As long as that number is a real number, we can deal with it. So it doesn't matter if it's rational or irrational. If we can plug in and we can get a number that makes sense to us, that will be the limit. Now, if you get something that's really weird, I would probably check it using a different method just to see, but that's what I would use first thing. If when you plug the number in, you get the indeterminate form, in other words, 0 over 0, infinity over infinity, or infinity over 0, if you get something like that, okay, then you're going to want to do some other investigations. First, I would try to do algebra. I would try to factor and see if anything cancels out to make it a little bit easier to deal with, and then re-plug in, plug that number back in, okay? If that still doesn't work and you get the indeterminate form again, see if there's anything else you can do algebraically first. If there is, then that's what you want to try to do. If not, then you'll need to move on to one of the other methods. Graphing is another method that you can use, but remember, if you're looking at a graph, you have to make sure it's approaching the same thing from both sides. It's okay if the thing that it's approaching is a hole in the graph. That's not a big deal, but it has to be approaching the same thing from both sides. It can't have a jump there somewhere, okay? So it has to approach the same thing from both sides. If there's an asymptote at the x value that you're approaching, then you need to look. The answer could be infinity or negative infinity, but again, you need to make sure they're traveling in the same direction, like either both up or both down. You can't have them doing this. If they're doing different things, then there is no limit. The limit won't exist, okay? And then for a table, if they ask me to do a table, I would do a table, but if they don't, that is going to be my last resort. I don't like tables because they're messy, they take a long time, and it's just not worth our time a lot of times, because most of the time, if the analytical doesn't work, graphing will. So I tend to only use a table when I have to, or when they've given me a table to plug into. Otherwise, I try not to use them unless it's necessary. In AP Calculus 110, we're talking about different types of discontinuities. So you need to understand what a discontinuity is. A discontinuity is any kind of jump or hole in the graph, or any kind of vertical asymptote in the graph. Those would all be considered discontinuities. There are two different types of discontinuities. We have removable and non-removable. Okay, removable discontinuities, when you learned how to graph rational equations in Algebra 2 and then continued your knowledge with that in pre-calculus, hopefully you learned from your teacher that sometimes you can factor the top and the bottom of that rational equation, and when you factor the top and the bottom, if they have a common factor that can be canceled out, then it's still a discontinuity in the graph, but it turns out to be a hole in the graph because you can remove it by factoring. You can cancel it out on the top and the bottom. And when that happens, it's still a discontinuity, but it's going to show up as a hole in the graph. Now, the problem with holes in graphs is if you do everything on a calculator, holes are not going to show up. So you have to understand how to show that there is a hole and how to remove the discontinuity there. If you don't know how to do that algebraically, you might get a lot of those wrong if you're relying on the calculator to do everything for you. So that is one caution that I would tell you about. So anyway, if you have a hole in the graph, it's removable. There are two types of non-removable discontinuities. Those would be jumps and vertical asymptotes. Now, hopefully from Algebra 2, you learned that if you have a vertical asymptote, that's going to happen when after you have factored the top and the bottom of your rational equation, nothing cancels out. If you've factored the top and you've factored the bottom and they have nothing in common, nothing that you can cancel out, then you're going to have a vertical asymptote at each of the factors that are on the bottom. You could have one vertical asymptote, you could have two, you could have three. There are just a bunch of different ways they can give you vertical asymptotes. Most of the time you will have one or two. There aren't very many equations that you have more than that, at least not ones that we will deal with. Okay? And then if you have a jump in the graph, this, for the purpose of calculus, when we have a jump in the graph, that's usually going to happen when we've been asked to graph a piecewise function. In other words, something like f of x equals maybe x plus 2 as x is less than or equal to -1, and then f of x equals x plus 5 as x is greater than -1. So that's a piecewise function where we're going to have a jump. The one function, the top function, is for one part of it, and then there's a jump in the graph at the next section of the x equals or x is greater than whatever the number is. So that is a jump in the graph. Now, sometimes with piecewise functions, you might have a piecewise that has two different parts, but the function is actually continuous, okay? If at that break in the graph, or at that break in the graph's equation, okay, that x value, when you plug into the first equation, maybe you'll have a hole in the graph, but then when you plug into the second function, the y value for that second function ends up being the same place, then the discontinuity is, I'll say it's removed. That doesn't really mean it's removed. It just means there is no discontinuity there because the y value at each of those functions or each of those portions of the function happens to be the same. So that's not a discontinuity at all. Your function ends up being continuous. Here's another example. This is what a continuous function would look like if it was a piecewise function. You might have something like the first function, let's say maybe it did this, and then the second function starts here, but then it's a parabola going up. So you see that ends up being continuous because we didn't have any kind of jump in the graph like this one has. Okay, and that's quite common in calculus, and we're going to learn how to determine values that will make a piecewise function continuous. This is AP Calculus 111, and in this one we're defining continuity at a point, and then we're going to talk about how you know if something is continuous at a specific point. So basically a function is continuous at x equals c, provided two things. F of c has to exist, the limit as x approaches c of f of x exists, and they are the same thing. Those three things have to hold true in order for that to happen. So I'm going to show you using a couple of graphs when a function is continuous at a point and when it's not. So if a function is continuous at a point, or if let's just say we want to know if a function is continuous. If a function is continuous, you're going to be able to draw that function without lifting your pencil. So if you can draw it without lifting your pencil, it's going to be continuous. Okay, so that's kind of a layman's term for what I just showed you in that definition. But here's an example of a continuous function. If you look at this, you can see that we could draw that function without lifting our pen or pencil. Okay, and then just looking at it in terms of how the definition was expressed to us. First of all, does f of c exist? Well, this is c right here, okay? And if this is my function f of x, then f of c would be this ordered pair right here. So this ordered pair is c f of c, the y value when we plug c into our function, okay? So this ordered pair is a solid dot. If it's a solid dot, then yes, it exists. Okay? Then it asks, does the limit as x approaches c of f of x exist? Well, what makes a limit exist? It has to be the same from the right and from the left. Okay, so from the left, the y value that we're approaching is f of c. From the right, the y value we're approaching is f of c. The limit at c exists. Okay? Then, are those two things the same? Well, yeah, it was a solid dot. The limit was the same at that dot. So this is an example of a continuous function. Now look what I have. I still have that same curve here, but it's got a hole in the graph, and I've got a dot right here. Can I draw that function without lifting my pencil? The answer is no. Okay? But sometimes they might ask you if it's continuous, yes or no, and then ask you why. So you might have to give a reason for why they're not continuous. Well, does f of c exist? Yeah, it does. It's right here. It's that ordered pair. Does the limit exist? Well, yeah, actually it does. The limit from the left is still this point. The limit from the right is this point. Remember, we said that it did not have to be a solid dot. From the left and from the right, it just has to approach the same number. Okay, so the limit there does exist. Are they the same? They're not. For this one, does f of c exist? Well, yeah, that's that solid dot right here. Does the limit as x approaches c of f of x exist? From the left, the limit is this number, this y value. From the right, the y value, or the limit, is this number. So the limits from the left and from the right are different. So no, the limit does not exist. Since the limit does not exist, we can throw that one out. What if I have this function? At c, I have a hole in the graph. There appears to be no place where there's not, or where there is a solid c value on the graph. That tells me there was a hole in the graph at c, a removable discontinuity. Does f of c exist? Well, no, it doesn't. There is no solid dot at c. Does the limit exist? Yeah, it does. The limit from the left and the limit from the right is the same. It is that y value, that whatever would be there, but it's a hole. It's a removable discontinuity. So since f of c did not exist, this one is not continuous. And again, could we draw that one without lifting our pencil? The answer is no. We can't draw that hole in there without lifting our pencil. So this one is not continuous. All right, next, they might give you an equation and ask you if that equation is continuous. This says, is f of x equals x squared plus 1 continuous? Well, I would just draw the graph and see what happens. If I plug in 0, I'm going to get 1. If I plug in 1, I'll get 2. If I plug in 2, I'll get 5. And that's enough to go on. I'm going to use symmetry to get the other side of my parabola. You should know enough about graphing functions to know that's a quadratic at this point. If you don't, you might want to do some research on that. So we've got a quadratic or a parabola there going up. There are no holes. I didn't have any place where I could have any asymptotes. I didn't have to factor and cancel out anything, so there are no holes. This is a continuous function. Okay? And they could ask us, what's the limit as x approaches 1? Well, we would say 2. What's the limit as x approaches a certain number? Is it continuous at that number? And you could do some investigation and decide, yes, it is. But as long as you can draw it without lifting your pencil, and they haven't asked you to justify it, it's a yes-no question. So don't try to go further than they ask you to. Just answer the question. Here I have 2 examples, and they're asking if the functions are continuous. Now remember, if the function is continuous, all you have to do is factor the function if possible to see if anything cancels out. It's not going to be continuous if there is any kind of hole in the graph or any place that the denominator of the graph would equal 0. If the denominator equals 0, then you have an undefined situation that would cause the graph to have either a hole or a vertical asymptote. So that's what I'm going to review here is when do you have a hole and when do you have a vertical asymptote, and how do you know the difference? We are not asked to graph this at all in these functions, so there's no need to graph them. We will talk about how to graph functions like this a little later, but right now all we need to determine is there any place on the denominator that x will equal 0? If there is, then we have to investigate further to see, can that hole or that discontinuity be removed? If it can be removed, then yeah, it's a hole. We need to state that it is a hole. If it can't be removed, we know it's a vertical asymptote. So we need to know the difference between whether it's removable or non-removable, because sometimes they might ask us that. Okay? So, are these functions continuous? If that's all they ask us, then all we have to do is see if there's a place on the denominator where x would equal 0. Well, so if I set the denominator equal to 0, in the first one, x equals 2. We have a discontinuity at x equals 2. Now, another thing they might ask is that discontinuity removable or non-removable? It's removable if this factor can be canceled out with a factor on the top, okay? So what I would always do with these, I wouldn't even bother with setting the denominator equal to 0 until I have simplified the entire fraction. So let's do that. I know that on top, that x squared minus 4 factors to x plus 2 times x minus 2, because it is the difference of 2 squares. My denominator was x minus 2, so I'm going to write it down on the bottom. Then I'm going to compare the top and bottom factors and see if anything can be canceled out. And yes, I have a situation here where x minus 2 can be canceled out. So that x minus 2 is gone now. So now if I were to graph that, I would just be graphing the function f of x equals x plus 2. I have removed the discontinuity. So when I do graph that, it would be a linear function with a hole at x equals 2. Looking at the next one. Again, I'm going to factor everything to see if anything cancels out before I decide whether we have any holes or discontinuities. So I'm going to, the x plus 1 won't factor, I just leave it. And then here, that's a trinomial. I'm going to see if I can factor that trinomial. A little review of trinomials. What factors of 3 subtract to give you 2? 3 and 1. So I know I'm going to have an x here, a 3, and a 1. The negative or minus sign here tells me the signs of these are different. And the minus here tells me the big number gets a minus. So the 3 gets a minus, the 1 gets the plus. And then look at what we have. The x plus 1 cancels. We still have a discontinuity when we set that equal to 0, but that discontinuity is a hole. Okay? So we still, if we set x plus 1 equal to 0, and we set x minus 3 equal to 0, when we solve these, this is x equals negative 1, this is x equals 3. The x plus 1 could be removed. So at x equals negative 1, we don't have an asymptote, we have a hole. If it's a hole, it's a removable discontinuity. So we have one removable discontinuity at x equals negative 1, and we have x equals 3 that did not cancel. If it doesn't cancel, that's a vertical asymptote. Vertical asymptotes are non-removable discontinuities. So we had 2 discontinuities here, one removable and one non-removable. And that's what they're going to ask you to solve when you're doing questions like this. And then eventually we'll move into, we'll find horizontal asymptotes and vertical asymptotes and holes, and we will graph those functions on a coordinate system and answer some questions about continuity, differentiability, and things like that.